All right. It is 12 o'clock p.m. here in Michigan, 9 o'clock in the morning over on the West Coast where headquarters is based. And that means it's time to get started. So, welcome everyone, and thank you for joining today's webinar, How to Verify Ethylene Control in Your Storage Environment with Felix Instruments. I'm excited to share how real-time ethylene monitoring can take what has traditionally been a slow manual validation process and turn it into a fast, data-driven, and continuous one. During the session, we'll discuss why ethylene control verification is such an essential part of post-harvest management, the limitations of conventional validation methods, and how continuous monitoring enables precise optimization of abatement performance. And we'll also walk through a real world case study where continuous ethylene data was used to refine an abatement system in a large retail produce cooler and show how that process led to a measurable improvement in product outcomes. So let's get started. As I mentioned, my name is Galen George. I'm the Director of Applied Science at Felix Instruments. My background is in biochemistry and food science. And for the past nearly 7 years, I've worked with growers, researchers, and engineers worldwide to apply real time gas monitoring to real world state storage environments. A lot of my work focuses on bridging that gap between what we can measure in a lab and what's actually happening in a commercial setting, helping teams take data and use it to make operational decisions that protect product quality. The approach we'll discuss today was built through exactly that kind of applied work, combining precision instrumentation, continuous monitoring, and controlled variable testing to move from assumption to evidence. Now, before we get started, we have a couple of housekeeping things to talk about. If you do have a question throughout this session that pertains to the content of this webinar, then please use the Q&A function in Zoom. That is what I will be checking at the end of the webinar, and I will be going through those questions to answer as many as I can. If you do put that question in the chat, then I will likely not see it. So please, if it's a question pertaining to the content of the webinar, keep that in the Q&A function. If there is some kind of technical issue, if my audio cuts out, if the slideshow isn't moving forward to the correct slides, things like that, then please let us know in the chat. Hunter Weber, our marketing coordinator, is moderating this webinar, and he will be moderating that chat and letting me know if there's an issue that comes up. He'll also be posting any relevant links in that chat. So if there's a link in the presentation, he will post that in the chat so that you can actually have something to click on and navigate to. So let's get started with the webinar. Ethylene, as most of you know, is a small hydrocarbon gas that functions as a plant growth regulator. And it's one of the most active signaling molecules that influences post-harvest physiology. It accelerates a cascade of processes, respiration rate, cell wall softening, pigment development, and loss of chlorophyll, all of which drive senescence. Now, even small concentration changes in the storage atmosphere can alter metabolic rates significantly. At just a few parts per billion, ethylene can induce measurable ripening responses. And at a few tenths of a part per million, you can begin to see visible color change or firmness loss within days. And that's why ethylene control is central to maintaining consistent quality. Temperature and humidity management are necessary, but they are not sufficient if ethylene accumulation is uncontrolled. When ethylene exposure drifts upward, even slowly, it shortens shelf life and amplifies variability. So verifying that your control or abatement systems are maintaining a low, stable baseline isn't just a technical formality. It directly determines the physiological stability of the stored product. And without verification, it's impossible to distinguish between an effective system and one that's merely operating. So most facilities still treat ethylene validation as an occasional task, something to check off rather than monitor continuously. Typically, an abatement system is installed, it's assumed to be functioning correctly, and occasional grab samples are used as reassurance. But ethylene systems, like any environmental control process, are not static. Filter efficiency can degrade, air circulation patterns can change, and loading behavior can alter the spatial distribution of gases. Without visibility into these dynamics, performance drifts silently. We've seen many cases where the average ethylene level looked acceptable in spot checks, but continuous monitoring later revealed regular spikes, sometimes lasting hours, that were completely invisible to periodic measurements. These kinds of transient events are exactly what accelerate product aging. And because they're unmeasured, they're also unmanaged. The lack of continuous feedback is what keeps teams from realizing the full value of their abatement systems. What both R&D and operations teams truly need is resolution and continuity, not just isolated data points, but a complete temporal profile of how ethylene behaves under real working conditions. They need continuous data showing how levels evolve throughout the day and week, feedback that reflects actual product conditions rather than ideal test scenarios, and the ability to quantify improvement objectively when operational changes are made. For R&D, this means you can evaluate abatement performance empirically, how fast it removes ethylene, how stable it remains over time, and how environmental variables affect it. For production, it means you can adjust system operation, change a filter, move a unit, alter a fan setting, and immediately see whether that adjustment improved or degraded control. And so that is the shift from manual confirmation to continuous optimization. Historically, ethylene validation relied on technologies designed for laboratory accuracy and not operational responsiveness. The most common approach is bag sampling followed by gas chromatography, which is an excellent analytical method, but it's slow, it's expensive, and disconnected from real time behavior. Another common tool is the colorimetric detection tube, which is a convenient and portable solution, but it's only semi quantitative. It's very heavily operator dependent and it's insensitive at the sub part per million levels that matter the most. And then, discrete grab sampling, taking one or two readings per day gives a rough average, but misses nearly all variation. And each of these tools serves a purpose, but none provide the continuous resolution needed to characterize dynamic ethylene behavior. The limitation of traditional methods is that they capture moments, not patterns. Imagine taking one snapshot of a moving object each day and trying to describe its speed or trajectory. That's essentially what single point ethylene measurement does. The cooler might look stable based on a morning reading, yet ethylene could spike dramatically each afternoon as restocking or door openings or airflow interruptions occur. These transient peaks are short, but physiologically they're significant. They drive ethylene signal cascades within tissues and can offset days of otherwise good control. Because static methods miss those peaks, they tend to underestimate total exposure, the integrated concentration over time, or what we call the area under the curve. And that's the metric that truly determines the product's ethylene stress load. So while traditional methods can confirm presence, they cannot characterize behavior. Continuous second by second data resolves that gap completely. So with continuous monitoring, we can see both baseline behavior and transient events simultaneously. We can correlate ethylene fluctuations within operational activities, things like fan cycles, restocking periods, temperature transitions, and understand why spikes occur. This turns ethylene control into a closed loop process. You measure, you adjust, and then immediately confirm the effect. It also enables proactive tuning. Rather than reacting to poor quality outcomes weeks later, you can identify problems as they develop and adjust abatement operation or airflow before they affect production. This is where real time monitoring moves beyond validation, it becomes process optimization. At Felix Instruments, we provide an integrated framework that supports this full workflow from portable research analyzers to fixed continuous monitoring systems. The F940, F950, and F960 analyzers measure ethylene alongside other gases like CO2 and oxygen, which allows users to study gas balance and respiration behavior in addition to ethylene accumulation. The F900 portable ethylene analyzer combines a 0 to 10 ppm sensor with a 0 to 200 ppm sensor, which provides both high sensitivity and wide dynamic range. For fixed single point applications, something like the Interscan Gas D8000 or Gas D1 systems use a proprietary interchangeable sensor cartridge system that utilizes a filtered 0 to 10 ppm ethylene sensor, which ensures continuity and consistency across all instruments. And the AccuStore and AccuStore Solo systems deliver continuous networked monitoring, collecting second by second ethylene data from multiple points across a storage environment. So, together, these tools create a structured path from research to continuous validation. When selecting a monitoring approach, think of it as a progression. So for laboratory or R&D validation, the F900 offers accuracy and repeatability that's needed for controlled trials. For something like an operational audit or a field assessment, the F940, the F950, or the F960 series provides rapid multi-gas analysis to identify ethylene hotspots or ventilation issues. For the continuous room level monitoring, the AccuStore system provides high resolution trend data and allows multiple points to be integrated into one live network. And for permanent single point verification, the Gas D8000 offers a stable and industrial grade solution requiring minimal maintenance. In most facilities, they'll start with portable verification and then expand into continuous monitoring as they refine their ethylene control strategy. Now, let's move into a real world example that demonstrates how continuous ethylene monitoring can reveal actionable information you simply can't get through manual or static validation. So, this case study comes from a high throughput retail produce cooler, which is an environment designed for rapid turnover and daily product movement. We conducted 14 weeks of continuous ethylene monitoring using our AccuStore system, recording one data point per second across multiple sensing nodes within the cooler. The data you see here on the slide represents weeks 8 through 14 of the ongoing study, the portion where we transitioned from baseline to abatement and then into progressive optimization. For the first 3 weeks of this period, there was no active abatement. The cooler operated under normal commercial conditions, full product inventory, routine stocking and retrieval, routine door activity, and airflow management exactly as the customer would normally run it. So no variables were being changed during this time. This gave us a true unaltered baseline ethylene profile under steady state operating conditions. During that non abatement phase, several consistent patterns emerged. We observed a distinct daily ethylene spike occurring almost every afternoon at roughly the same time each day. The amplitude and timing were highly repeatable, suggesting a predictable operational cause rather than random noise. And then, given this was a retail environment, the most probable contributors included things like foot traffic, movement of product in and out of the cooler, and temporary disruption of airflow circulation near entry and exit zones. These are all common in such facilities and often coincide with elevated ambient temperatures or localized stagnation that allows ethylene to accumulate transiently. Outside of those afternoon periods, baseline levels remained relatively stable, but when we integrated the data, calculating total exposure as area under the curve, it became clear that this single daily spike accounted for a disproportionate share of total ethylene exposure across each 24-hour cycle. In other words, it wasn't the steady background level doing the most damage. It was these short, high intensity ethylene events that were driving the overall stress burden on the stored produce. So after establishing this 3-week baseline, we introduced the first abatement system, a standalone, continuously operating unit, and began measuring the system's effect in real time. Once the first abatement unit came online, the response was immediate and clearly visible in the data. The average baseline ethylene concentration dropped by roughly half compared to the non abatement condition, confirming that even a single continuous scrubber was effectively lowering the steady state of ethylene load within the room. However, that daily spike persisted almost unchanged. The magnitude of those peaks remained high, indicating that the single unit's air exchange rate and capture capacity were sufficient for background control, but not rapid enough to neutralize sudden bursts of ethylene generation or redistribution. And to understand this behavior more completely, it's helpful to consider how ethylene behaves in a mixed air environment. Ethylene has a diffusion coefficient similar to carbon dioxide, but in cool, high humidity conditions, local mixing is often limited. So when warm, ethylene rich air enters during stocking or loading, it tends to rise, following both temperature gradients and airflow vectors from the entry. And that's exactly what we confirmed through earlier mapping data. So prior to this 6-week case study window, we had used multiple AccuStore sensors deployed vertically throughout the cooler to characterize ethylene stratification. And what those measurements showed was that ethylene concentrations were highest in the upper third of the room and lowest near the floor. Once we transitioned into spatial sampling, we also identified zones of consistent ethylene retention. So typically corners or areas near ceiling obstructions where air velocity was low, and these pockets kind of act like reservoirs, slowly leaking ethylene back into the general airstream long after a loading event ends. So you can see on this graph here on this slide that we have 3 different kind of spatial locations, each a different color line on this time series plot. And you can see that the green, which is the southwest corner, is consistently a much higher peak than the northeast or northwest locations of the sensors in this cooler, which are very, very similar. And so we were able to, with that knowledge, kind of look into what's going on with that one corner of the room. So, armed with all this knowledge, after 2 weeks of single unit operation, we introduced a second abatement unit, and that unit was positioned deliberately to target the upper third of the room and the spatial zones that had shown the highest ethylene concentrations in the baseline data. The second unit effectively increased both the total air throughput and the distribution coverage, which improved scavenging efficiency for both baseline and transient ethylene peaks. And you can see in this graph as well, so you'll see this major spike that occurs. It's a clear inflection point. After the second unit came online, you can see from pre-abatement to the first unit to the second unit, the amplitude of that afternoon spike has been decreasing sharply. So we started off at almost 4 ppm with our highest spike in the non-abatement period, averaging around up to 3 ppm for these single unit abatement peaks, and then getting down to 2 for our highest peak in the with the 2 units in that room. The total daily exposure, which was measured as the area under the curve, also dropped even further. And the overall variability of the signal, what we call ethylene noise, was significantly dampened. We also saw improvement in the rate of decay after each spike event, So in the baseline data, ethylene peaks often lingered for hours before returning to baseline. But with this dual abatement, the decay constant increased substantially. So the room returned to equilibrium much faster after each disturbance. This reduction in persistence is just as important as peak suppression because it directly lowers cumulative exposure and minimizes ethylene triggered physiological responses within that produce. Since then, the team has continued to fine tune our system configuration. The air intake height of both of the units has been raised to further target the upper air mass, where ethylene tends to concentrate first. Each change that we make is introduced individually and then observed over several weeks of continuous monitoring to isolate variable effects. And this controlled single variable iteration is what allows continuous monitoring to serve as both a diagnostic and an optimization tool, something that static testing simply can't accomplish. So, by the end of this 14-week study window, the progression from non abatement baseline to dual abatement configuration yielded very clear and quantifiable outcomes. So, our total ethylene exposure, or that area under the curve, decreased by approximately 40% relative to the baseline. This means the integrated concentration over time, essentially the product's ethylene dose, was reduced nearly by half. The baseline ethylene concentration dropped by about 50%, which provides a more stable, low ethylene atmosphere throughout the storage period. And the daily ethylene spike amplitude was cut roughly in half, while the decay rate after each spike doubled, indicating faster recovery to baseline conditions. These are substantial changes for an operational environment of this size, especially considering that the abatement system itself was never modified, really. It's only optimized in its placement and its airflow configuration. From a physiological standpoint, these reductions translate to a markedly lower ethylene pressure on the stored produce. That means reduced expression of ethylene responsive enzymes, slower softening rates, and delayed color development, all leading to longer shelf life and better product uniformity at retail. It's worth noting that these improvements were achieved under real world conditions, not a controlled chamber, but a functioning, high traffic retail cooler with all the variability that entails. Continuous monitoring allowed us to capture and interpret that variability, turning it from background noise into actionable information. And that's the key takeaway here. So without continuous data, this level of optimization would have been impossible. We would have seen average concentrations drop with the first unit, declared success, and then missed the opportunity to cut total exposure nearly in half. Instead, with second by second resolution, we could track baseline, spike behavior, decay kinetics, and spatial gradients simultaneously and use that insight to make targeted evidence based adjustments that demonstrably improved ethylene control performance. This study remains ongoing, and further iterations are already in motion, such as refining intake height, adjusting directional flow, evaluating whether localized circulation fans can further flatten those vertical gradients. But even at this stage, the data illustrates exactly what continuous monitoring enables. It's a quantitative, iterative approach to ethylene management that not only verifies performance, but drives continual improvement. So this example really captures like the value of continuous measurement. It's not just about confirming that an abatement system works, right? It's about learning how it works in your specific environment and how to evolve that setup over time to keep pushing ethylene exposure lower and product quality higher. So, how do you apply this kind of workflow in your own operation? I would start simple. I would use a handheld analyzer like the F900 or the F94 U50 or 60 to benchmark ethylene levels across different zones in your doors and your fans and your product stacks. And then once you've identified areas with the highest variability, add one or two continuous monitors in those locations. After collecting a few weeks of continuous data, you can then identify your baseline patterns and watch for regular spikes or zones of high accumulation. And then you can begin making controlled adjustments, one variable at a time, and measure those impacts of each of those changes. Over time, this iterative process will produce both lower overall ethylene exposure and more stable environmental control. That stability translates directly into improved product condition, reduced shrink, and more predictable shelf life. So to summarize, you can't control what you can't see. Traditional validation methods provide only fragments of the ethylene picture. Continuous monitoring shows the full story, revealing when, where, and why ethylene fluctuates. And with that visibility, you can align abatement to ethylene behavior, quantify improvement, and then maintain control with confidence. The result is measurable, reduced exposure, improved consistency, and longer lasting product quality. So thank you guys all for your time and attention today. If you'd like to learn more about any of the instruments I discussed, whether it's the F900, the AccuStore or the GasD or the multi-gas analyzers, please feel free to reach out to us directly. You can contact us via email, sales@felixinstruments.com. You can go to our website felixinstruments.com, or you can connect with me after the session. If you do have other inquiries, then feel free to just send us an email. You can always call us as well. Our phone number is listed on our website. And we're happy to always also to have visitors. If you happen to be in the Pacific Northwest, you can come by and talk to us in person. So now I'm going to open this up for any questions about ethylene control, validation design, or data interpretation. So I'm going to go ahead and open up the Q&A function here. And the first question that I see is how much air has to move through the sensor to get an accurate read? So this is a great question. This actually brings up the idea of the base technology being used and the theory behind the technology being used. So in electrochemical sensing, which is what we do, there are passive electrochemical sensors and there are active electrochemical sensors. Passive sensors are ones where an external airflow is required to pass into that sensor in order to get a reading. Everything that we make is active sensing. So all of our instruments have a built-in pump that actually actively draws air in. And that way we have a controlled flow of air that is consistently moving into that sensor so we can get really highly precise and selective measurements. So every instrument has a slightly different flow rate. But in general, you won't need to actually force air into the instrument. It will actively pull its own air in via the integral pump. That's a great question. Thank you. The next question I see on this list is, if you follow the ethylene production on a continual basis and you see spikes, what can you do, as it is hard to use a device to control the ethylene levels? So we monitor, and then what? This is a great question. So in the case of this case study that I showed you, we were working in conjunction with a company that creates abatement technology, and they were wanting to optimize and test that in a real world scenario. And there are lots of different abatement technologies out there. There are abatement technologies that are reliant on things like potassium permanganate, which has long been used as a ethylene scrubbing chemical. So it's basically, it'll be some kind of media that's impregnated with potassium permanganate, which sequesters that ethylene as air is passed through it. And so it basically acts as a giant filter in line with a intake, and then it shoots the air back out after it's been kind of cleaned of ethylene. There are other technologies that use more advanced things like UV light or ozone or other kinds of abatement techniques. There's lots of companies out there that do this kind of stuff. So what I would say is, if you are doing your monitoring as you should and identifying the issues in your environment. After you have identified those issues, you can then go to and shop around at different companies and present to them your data and say, here's what we're dealing with. Here's our room configuration. Here's the variables that we've identified as being problematic. We're seeing a spike during these times, and we think it could be A, B, or C. And then from there, you can, go in there with a lot more confidence, knowing that this company that you're trying to, test their abatement technology, will have your best interest in mind, will understand your situation, and will be able to actually mitigate that ethylene in those, in those problematic areas. So yeah, so I would recommend is just look around for other abatement technology companies and make sure you go into it with some data and not just go and say we have ethylene, we need to get rid of it and hope for the best, which is typically what has been done in the past. And then this last question that I see in the Q&A is any idea why the spikes occur in the first place? Yeah, spikes can occur for a large number of reasons. In the case study here, this was a retail produce cooler, so it's a cooler that's open to the public where when they're shopping, they're going in and they're grabbing produce and taking it out. There's also lots of operational, variables in there with restocking and opening doors to get in and out. And so with something that a room like that isn't a controlled atmosphere, sealed environment, you have lots and lots of changes to airflow patterns. You have outside air coming in, you have inside air leaving, a lot of air exchange. You have people moving produce in, maybe high ethylene producing produce. You have people that are taking produce out of that cooler. So you're removing the total potential exogenous ethylene being released. Um, there's lots and lots of potential, you know, reasons behind why that spike could occur. Those spikes in the idea of other post harvest applications throughout the supply chain, like I mentioned, a controlled atmosphere room, say like where you're storing apples for months on end, right? Where it's completely sealed, you have a controlled atmosphere, um, and in those cases, you have less of those problems to deal with. I would say it's a little bit more of a controlled environment, hence the name controlled. But uh, the idea is that you can still get random spikes due to just release of ethylene from the fruit, unless you're actively controlling, through things like 1-MCP or other kind of treatments like that. So yeah, like, there's lots of reasons why they could occur, but that's a great question. Thank you for that. And we've got one more here. Actually, it looks like. Great question from Rob. What is the impact of formaldehyde on the readings? Can it be falsely picked up as ethylene? Right. So with electrochemical sensing, this is a great question. With electrochemical sensing, there is always a slight risk that there are cross sensitivities, right? That there are gases that can provide a false signal for a sensor. So even if it's an ethylene specific sensor, there's potential that interfering gases might be present and they might give a false ethylene reading. Typically, those gases it's mostly alcohols and or carbon monoxide. Formaldehyde isn't as big of an interfering gas. However, we use filtered ethylene sensor that actually has an onboard filtration system specifically designed to remove the impact of those interfering gases. And so it is a very highly selective and highly sensitive ethylene sensor. And so I would say the impact of formaldehyde will be minimal, if not zero, on the readings for our with our sensors specifically. With other electrochemical sensors, might not be the case. Depends. You'd have to talk to the manufacturers for that information. But great question. All right. Well, it looks like that is all of the questions that are in the Q&A. If you do think of something later in the day or later on, just feel free to shoot us an email. We're happy to help answer questions. You can also book a product consultation with me on our website. There's a link to schedule a product demonstration. If you click that, you'll be taken to a link that allows you to book a time to have a video call with me if you want to talk further. If you specifically are interested in kind of establishing a continuous monitoring system or just integrating better ethylene monitoring into your post harvest environment, then feel free to reach out. We're always happy to talk. So it's great seeing everyone today, and thank you so much. Have a great rest of your day.